Okay, so let's start with an example. And the first example is going to be one where it should be very obvious that the disk method is not the way to go. So this is example 1. The region that we're going to be looking at is the region that is contained between the x-axis. So our region is between the x-axis and the curve y is equal to 2x squared minus x to the third. So I'll draw that. And then we'll try to decide, based on our picture, why we don't really want to have to deal with this in the disk method. Okay, so why not this? Why not this with disks? We're going to take this shape and let's say we're going to rotate it around the, I guess I have to tell you the axis of rotation as well. So we're going to rotate this about the x-axis. So the first question when you're looking at a problem like this is, why not disks? The reason that you know you're not looking at disks here is when you try to draw what the disk would look like, you end up with a shape that touches the same curve twice. Now, in the previous example, when there was a square and a square root involved, it's very easy to move back and forth between y as a function of x and x as a function of y. It is, in general, not very easy to move back and forth when you're dealing with cubic functions. Okay? So in order to use disks on this thing, I would need to give you a y value, and you'd have to tell me the x value, which means you have to invert this function. That's not something that you're going to want to do. Okay? It's usually a good hint that you're working with the wrong method when the top and bottom of your rectangle are on the same function. So we're not going to use disks on this. We're going to try to use shells instead. Okay, so no disks. Instead, we'll use shells. So to use a shell, we draw our skinny rectangle in the other direction. And then what we're thinking is that's the rectangle that we're going to rotate around the x-axis. Okay? Now, you should decide right away if this is appropriate. Well, this rectangle, no matter where it's located inside here, the same curve is always on the top no matter where I'm at. And the same curve is always on the bottom no matter where I'm at, which means I've got a consistent definition of the height of this rectangle. So the only other thing I need to know is, where are these intersection points? The region that I'm rotating is this region. So when I'm cutting my slices, I need to know where to stop and where to start. So I need to know those 2 points. Okay, well that's easy enough. 2x squared minus x to the third is equal to 0. X squared times 2 minus x is equal to 0. So this happens at x equals 0 and x is equal to 2. And that's all the information that we need in order to build a shell model for this volume. Okay, so let's do it. So we have this region, and we know we've got this curve, which looks like y is equal to 2x to the third, or 2x to the second, minus x to the third. I know my typical rectangle is here. I know I'm rotating it around this axis. So that means the first thing I'm going to find is my radius. So my radius for this problem, r, my radius of rotation, is x, because that's the location of the rectangle, minus 0, because that was the point that we rotated around. So it's just x. After all, a rectangle that's x units away from the x-axis is x units away from the x-axis. Okay, so now what's the height of the rectangle? Well, the height of our arbitrary rectangle, or representational rectangle, is going to be h is equal to 2x squared minus x to the third, because that's the top curve, minus 0, because that's the bottom curve. Finally, I need to know the depth of the shell that's coming out. So the depth is equal to the width of this rectangle. Well, since it's skinny in the x direction, this is delta x wide. If you like, what we've done is we've taken that rectangle, we rotated it. The rectangle is right here. We took that rectangle and we rotated it around the x-axis. And then we cut it and laid it out flat. And what we're saying is that the length of this rectangle rectangular parallelepiped, is 2 pi x, because that's the circumference of the shell, because the radius was x. The height of it is equal to 2x squared minus x to the third, and its depth is delta x. And so the volume of a shell here, V, is equal to 2 pi x, 2x squared minus x to the third, delta x. That's enough actually to get you your integral, because we have all the pieces that we need now. We know that we start slicing at x is equal to 0, and we finish slicing at x is equal to 2, which means when we're adding up our shells, we start with shells at 0 and we finish at 2. That tells us the location of the rectangle that determines the shell once we rotate it around. Then we just stick the formula for the representational shell in there. 2 pi x, 2x squared minus x to the third, dx. And all we need to do from this point is to compute the integral. So the big bulk of the problem here is actually getting to the point where this integral is set up. All of the hard work in a problem like this is supposed to be in setting up the model for the integral. And the techniques that we're going to learn in the class and that we've learned already are just supposed to help us figure out what this is. Okay? So the creativity and the pictures and the modeling is in building this. And you should be able to look at that and believe that what you've written down represents the geometry here, right? This is just that. This equation is that volume. All right, so pretty standard integral here. It's just going to be polynomials. Remember that when you're dealing with integrals, you have to multiply everything out first before you do it, okay? So I'm going to pop the 2 pi out front and then multiply the x in. That gives me 2 pi times 2 over 4 x to the fourth minus 1 over 5 x to the fifth, evaluated from 0 to 2. When you punch through and you grind out the numbers, I think what you end up with is, let's see, 2 pi, so there's a 1/2 and then a 16 minus 1/5 times 32. And when the dust clears, what you should get is 16 over 5 pi. Okay. Even up to this point, though, for me, remember, that's sufficient. Because when you get a numerical answer, you can always check your numerical answer against the book's numerical answer in something like Wolfram Alpha. So, how do you decide which method to use? Whichever way gives you the rectangles that you like. If you have a function that folds over on itself, you want to avoid having to use that same function as the top and bottom or the left and right of the rectangle. All right, so let's look at another problem here, and we'll decide which way we want to do it. Sometimes we can use either method and it doesn't matter. So here's example 2. So let's suppose that we're looking at y is equal to root x, x is equal to 4, x is equal to 0, and the x-axis. That's the region. And we're going to rotate it about the, I don't know, x-axis. Okay. So what are we asking for here? All right, so there's y equals root x. I know that I'm going out to x is equal to 4. I started at x is equal to 0. I've got the x-axis on the bottom, and so what I'm doing is I'm taking this region right here, and I want to rotate it this way. What sort of rectangle should I use? Well, in this one, it doesn't matter. You can choose either way, whatever you're more comfortable with. I'm going to show how to set this problem up 2 different ways, both in the washer method and in the shell method. And the answers are the same, because the volume doesn't change no matter how you compute it, but the setups require different ways of thinking. So first, let's look at it with the shell method. So let's start by looking at shell method versus the disk method. In the shell method, we're going to think about this thing as having rectangles that are cut like this and are rotated this way, so that the representative shapes that you get out are little skinny pipes that look like this. Okay? And the sort of volume that you're going to end up with is going to be the volume of a figure that looks like that. So what are the different things that we need to know? Well, you know that this is going to be a dy integral because the location of the rectangles is y values this time. Everything is derived from knowing a y value. So the volume of the shell this time is going to be a right minus left type setup because the rightmost function is the top and the leftmost function is the bottom. So what are those going to be? In this problem, this is given by x is equal to 4, and any rectangle that you draw, the bottom curve is y is equal to root x. But remember, I'm giving you y values and you need to tell me x values, which means you need to turn that into x is equal to y squared. So the height of any one of these rectangles is going to be 4 minus y squared. What's the thickness of the shell? Well, it's delta y because it's skinny in the y direction, okay? And so the volume of a typical shell is going to be v is equal to 2 pi times the radius, which is this distance right here. That's r. But that's obviously just y because you're rotating around the x-axis. You go up y units to get to the rectangle. So the radius is y. 2 pi y times 4 minus y squared delta y. That's the shell. And then you're going to add those shells up with y values that start at 0 and end at 2. And you know that's 2 because this point right here is the point 4, 2. So you're going to go from y is equal to 0 to y is equal to 2. And that's all the information you need to build the integral. On the other hand, if you're going to do this with disks, well, disks run this way. So you take your skinny rectangle and you roll it around this way, and what you get out that is this sort of coin shape. So the volume of the coin shape, well, what are all the dimensions you need here? Well, you're going to need a radius, and you're going to need a height, because you're going to use the cylinder formula. So the radius this time, so the radius is this distance right here. So the top function is y is equal to root x. Why y is a function of x? Because the rectangles are located at x values. So I'm telling you x information, and you need to tell me y's. So I need to work with y as a function of x in this setup. So the radius here is root x, because that's the distance you go from the x-axis up to the function. Okay, so the base area in this case is given by the formula pi r squared. And so you know that the base area is pi times the radius that you just discovered, which is root x squared. And so the volume of the typical disk is pi x delta x. And then where did you slice? Well, we started slicing at 0. We finished slicing at 4. So we go from x is equal to 0 to x is equal to 4. Okay. So what I'm saying here is I start cutting at 0 and cut, make my rectangles until I get to x equals 4. And each one of those rectangles, when it gets spun around, turns into one of these disks, and the disks have this volume. In this problem, you start cutting at y is equal to 0 and cut up to y is equal to 2, but now you're spinning it flat this way, so you end up with this shell shape instead, whose typical volume is given by this, because of that trick where you cut it and think of it as a rectangular parallelepiped instead. Okay, so these two integrals turn out to be, of course, exactly equivalent to each other, unsurprisingly. So the typical volume here, so we started at y is equal to 0, we finish at y is equal to 2. Our typical volume of the shell that we were adding was 2 pi y 4 minus y squared delta y. And over here, we went from x is equal to 0 to x is equal to 4, and the volumes that we were adding up were pi r squareds delta x. So we can write down two different integrals for this. So this is the integral from 0 to 2 of 2 pi y 4 minus y squared dy. Here, it's the integral from 0 to 4 of pi x dx. So it's not always possible to tell when you go in what the easier formula is going to be. It's obvious in this case that the disk integral is a significantly easier to compute integral than the other one. In many cases, it's going to be the case that the shell is going to be an easier way to work. Okay, it's not always the case the disk is easier if you can do it. It has to do with the structure of the function that you're dealing with. So this is pi x squared over 2 evaluated from 0 to 4, which is 8 pi. On this side, you have the integral from 0 to 2 of 2 pi 4y minus y cubed dy, which is 2 pi times 4y squared over 2 minus y to the 4th over 4 evaluated from 0 to 2, which also turns out to be 8 pi. Okay, so you should expect that these volumes are equal to each other. In practice, what matters here when you're doing this is that you're consistent about your approach to these things. When you're looking at a problem, like the problems we're just looking at, you need to make a decision about, okay, is it going to be better if I set up my rectangles this way and go around to make disks, or if I set up my rectangles this way and I go around to make shells instead? Okay. Sometimes it doesn't matter, like in this problem, because no matter how you set up your rectangles, the same curve here is always on top as on bottom, and if you go this way, the same curve is always on the right as is on the left. So as long as the rectangles are consistently defined by single functions, that's the ideal situation for using a method. So unless I specifically tell you a method, just stick to the one that seems obvious. All right, so go practice. These things are much easier to do once you've had the opportunity to work on them. All right, see you.